Yep, looks like we're recording. Good, so welcome back, everyone. I will admit it completely slipped my mind to check the video of the syllabus lecture we had the other day. I'm still planning on making a new playlist on my YouTube channel just for this semester, and I'll try to take a look at both this video and the last one this afternoon. I'll be back this evening for my evening office hours in the evening lab that I have to supervise. So I'll try my best to get that done before then. I should have thought of it because I just want to make sure that everything's working. Not quite sure what I'll do if it's not working, but I guess we'll cross that bridge when we get to it. What other announcements do I have? You might have noticed that I've started setting up OWL. Again, like I said, there's nothing due on OWL this week that's graded. The only thing that's due on Friday is the introductory assignments, which are not graded. I'm not sure if I've said this before, because forgive me, but I have 3 classes in 2 different subjects. But if the assignment says not graded, you can always trust that. I will never, ever change not graded to graded. I give you my word. You can always trust that. Even if it's one that I had meant to be graded and it's to my detriment to leave it not graded, I will leave it not graded. You can always trust that. I have to wonder what it really means for something to be due on, say, Friday when it's not graded. But I do recommend you take a look at the introductory assignments. I recommend you take a look at all the assignments that are not graded. There's probably going to be something there that's helpful. In this case, it will show you what types of questions you can expect, how to know what you need to know in order to answer the questions, and how to answer the questions and get credit for it. It's stuff like that. And I also, you'll probably have noticed, put up the chapter 1 assignments. So they will be due a week from Friday on the 10th, because by then we should be done with chapter 1. So I guess the main thing I should say about OWL is please don't let it wait until the very end. I don't consider myself responsible to sit on email all Friday evening and drop everything at a moment's notice like that. So I do have my office hours tonight. I have office hours tomorrow, or the day after that. Wait a minute, today is Wednesday. Yes, I have office hours on Thursday as well. So you can feel free to come and see me with any questions. Oh, well, of course, I don't think there's going to be very many questions about the introductory assignments, but next week, I have all my office hours next week. I realized I promised you guys cat pictures. What am I doing? Terrible, professor. I got them ready. Goodness gracious. Where did I put them? In here, maybe? Yes, I see some cat pictures in there. So, awesome. I guess it won't let me do it. That's a shame. Will it let me do it for any of these? What do you mean invalid value? You don't need registry for pictures on a USB drive. Well, that sucks. Can I say that here? Too late. I'll have to figure out a way around that because you need to see my 2 cats or my cat and my dog, depending on how you want to look at it. One thing I will say, pictures aside, generally one thing I like to do at the end of the term is we have Bella Day. Bella is my cat that thinks she's a dog. Basically, she's dumb as a rock and loves everybody. So what I've been doing for a few semesters is I would bring her into my office. I usually would do it the reading day of finals week. And weather permitting, and also I don't mean to be macabre about it, but assuming there is still a Bella and she's in good health, we'll do it again this term too. I say that because she's over 15 years old. I'm absolutely amazed. I've never had a cat live this long. Seems to be doing fine. I don't know, just as dumb and happy as ever. So we can worry about that more towards the end of the term. But that's the situation. I don't really know. Why will it not open the simple JPEG file? I don't get it. Security sometimes baffles me. Okay, I'm trying to think if I have any other announcements. I guess we talked about exams. We did all that type of thing. So as things come up, I'll be sure to try to mention them. Good. So today we're going to start pretty slow. As I said, chapter 1 is mostly about reviewing those parts of Gen Chem, which Gen Chem is a prerequisite for this course, but it's those parts of Gen Chem which are especially important for this class, having to do with organic chemistry. I thought of another thing I should mention. I look over at my syllabus and I see the courses called Elements of Organic and Biological Chemistry. In case you were worried I forgot about the biological chemistry part, I did not. I am an organic chemist, so that's where my focus and attention normally lies. But your textbook does have chapters on the major types of biologically important molecules. So we have a chapter on nucleic acids, for instance. I'll assume you've heard of these things from high school biology. There's a chapter on proteins. There's a chapter on carbohydrates. There's one on lipids. And I think I might be forgetting one, but there are these biochem chapters. And we are covering them, but I'm going to cover them mainly from the perspective of organic chemistry, in terms of the context of the rest of the class that we're having together. By that, I mean we're going to focus mainly on structure, which you may have already discerned that we organic chemists are rather obsessed with structure. We're certainly going to talk about the reactivity of these molecules. And I don't know that we'll get too much into mechanism. Those three are sort of those three words are kind of my summary of organic chemistry. It's about structure, it's about reactivity, and it's about mechanism. We're not going to be doing too much with mechanism this semester. In general, a little bit. We'll talk about it a little bit starting in chapter 1, but I'm not going to go too heavy on that. Just because I only want to talk about it when I feel there's some benefit to you guys. But it's kind of an extra layer of information beyond what else we'll be discussing. Anyway, my goal with what we cover in the biochem chapters is going to be to get you ready for upper level biology or biochem classes, or biology classes where you discuss biochemistry. Where I think you will find in those classes that what they cover, maybe you've already had some biology classes. In that case, I'm sure you've had some. In that case, what we cover in here is going to put that material in perspective, because what we cover in this class is going to be exactly not what you will hear emphasized in those classes. So if you have maybe some upper level biology classes or medium level biology classes still to take, I think it will be good background for you guys, because they're not going to go over the structure of these things in any detail. They'll basically just throw up slides and say, learn it, live it, love it, which is understandable. You know, they have a different focus than we do in organic chemistry. So just rest assured, we also will cover those things in those biochem chapters. And really a similar chapter in spirit is the one we're going to end with on polymers, where we're going to take some of what we've learned and apply it to a particular type of molecule. So that's at the very end of the semester. And I also don't know if maybe some of you might be going into fields that are a little more geared towards the engineering or material science side. Those last 2 class days are for you, because we're going to talk about some pretty important materials and ones that you'll be dealing with whatever your field winds up being eventually. Good. So I think that's really all I need to say about that. So what I think we're going to start with is, I guess the story I'll start with is just about the basic structure of the atom, something which I almost think should go into the category of general knowledge. You probably went over that to some degree, even in your junior high science classes. So I'm going to assume that you come into this class, let alone your Gen Chem class, which you also had. But I'm going to assume you come into this class with some understanding of the structure of the atom, understanding that an atom of any element has at its center the nucleus of the atom, consisting of protons and neutrons, or in the case of hydrogen 1, just a single proton. But we call the protons and neutrons nucleons. They sit at the center of the atom. and nearly all of the mass of any given atom is there in the nucleus. And around that nucleus, in some sense, are the electrons. We have some density of electrons in certain spaces around the nucleus, and that's good enough. We don't need to get into quantum mechanical descriptions. I don't even really understand most of that stuff, and I see absolutely zero educational benefit to going into that detail with you guys. But if you have this idea that distributed around the nucleus of any given atom, we have these electrons that sit in these regions of space they call orbitals, which again, I'm assuming you've covered in Gen Chem. That's probably good enough. I don't think we need to get any more detailed than that. I think that's a perfectly good background. And I'm going to assume also that you've correlated the structure of the atom with the periodic table. That's one thing I should also say. You do not need to worry. With every exam, I will always give you a periodic table. I wouldn't dream of making anyone taking any chemistry class at any level, freshman, sophomore, junior, senior. I wouldn't dream of making them take a chemistry exam without a periodic table. I suppose I could even also put one up on the screen. I'll try to remember to do so, but I do plan to provide a periodic table with every exam. I guess while we're on the subject of exams, I'm also planning to provide scantrons. So at least that's my goal. I have to kind of look into that. We have quite a bit of time. It's not breathing down our necks. But I'm hoping to provide scantrons because I don't want any of us to deal with that headache on an exam day. So I'm hoping to come with both printed exams and scantrons. I don't want you guys to deal with, oh, I forgot mine, oh, I brought the wrong type. I want to spare us all that. So that's my hope, is to provide you guys scantrons as well. Good, so we can talk more about that as the time comes. But anyway, I think you've seen this guy before. I think you've seen the periodic table before. And you're aware, I assume, that the periodic table is laid out the way it is because it goes along with atomic structure, that we have these energy levels. And in fact, they correlate pretty much exactly with the periods, as they're called. Those are your rows in the periodic table. And so you have your first energy level, second energy level, third energy level, and so on. As the atom gets bigger and bigger, we have additional energy levels. And electrons in those energy levels will be at higher and higher energy as you go down the periodic table. And I'll also let you know, this being an organic chemistry class, we are going to focus on a pretty small subset of the periodic table. I do want to go over electron configurations a little bit. I think it's useful background before we start actually putting atoms together and make molecules. Are we going to be thinking every single day of the rest of the semester, 1s2, 2s2, 2p, whatever? No, I don't think so. But I think it's worth going over. I think it's useful background. You covered it in Gen Chem, so I assume you know it anyway. And it's also in your book. So I'm not going to spend huge amounts of time, but I just want to refresh our memory on that a little bit. But electron configurations really go hand in hand with how the periodic table is laid out. So you've got your energy levels, and in each energy level, you have subshells, and that's where these things we call orbitals sit, in the subshells. So you may recall, for instance, in the first energy level, all we have, and we'll do some examples of electron configurations in a moment. I'm just kind of setting the stage here. But perhaps you remember that in the first energy level, the only subshell we have is the 1s subshell, and it only has one orbital in it, the 1s orbital. And perhaps you also recall, because of things like Hund's rule and the Pauli exclusion principle, that you can only fit a maximum of 2 electrons in any given orbital. And that when you do put 2 electrons in an orbital may also contain 1 or 0 electrons. But when there are 2 electrons, they have to be of opposite spin. Electrons have a property called spin, which means they behave kind of as if they were tiny, hard rotating spheres. They aren't really, but they have a property that means they act kind of as if they were. So that's what they mean when they talk about electron spin. And so since there's only one orbital and we can only fit in 2 electrons in that orbital, that means we would expect 2 elements in the first energy level. Lo and behold, there are 2 elements in the first energy level, and that's it, hydrogen and helium. Second energy level, our first p subshell opens up. So you have the 2s orbital that can have up to 2 electrons. There you go, lithium and beryllium. And then comes the 2p subshell. There's 3 orbitals in the 2p subshell. And by the way, even that follows a pattern, right? You may recall this. In any s subshell, there's 1 orbital. In any p subshell, there's 3. In any d subshell, there's 5. So it's going up in odd numbers. That pattern continues. I can guarantee you we are never going to have to worry about F-block elements in this course. I don't think we'll have very much to say even about the D-block elements. And as you see, I can't help myself. I can't help pointing out where the D-block is in the periodic table because there it is. You know, it sort of jumps right out at you. We'll get there in a second, though. We're mainly going to focus on the main group elements, the ones with foliar partly filled S and P subshells. And really, as far as that goes, I think we're mainly going to be sitting around carbon. These main group elements here are going to be the main ones we talk about, that and hydrogen, of course. So I don't think we're going to mention cadmium very much this term. And I certainly don't think we're going to mention dysprosium. Well, I just did, but you know what I mean. I don't think we're going into the F block. I remember years ago, we were doing a standardized test with our students at my previous school. And on the front page of the standardized tests, I don't know if it was meant as a joke, they had this thing, periodic table for organic chemists. And it had like hydrogen, carbon, nitrogen, oxygen, maybe silicon, phosphorus, and sulfur, and some of the halogens, and that was it. So it kind of is true. Whereas you really took a broad view of the entire periodic table in your Gen Chem class, I can tell you right now, nearly all of the elements we won't even use in this class when we focus on organic chemistry. That's because we've said that organic molecules are those that have a certain amount of carbon and hydrogen in them. I don't know if I can give you a hard, bright line that separates organic from inorganic. But at some point, there's enough carbon and hydrogen in a molecule that it begins to take on this set of characteristics and reactivities that we associate with organic molecules. And I think even from everyday experience, you know something about that. You know that table salt, sodium chloride, is inorganic. It's a salt. It's water soluble. It will not undergo reactions like organic molecules do. Something you use on a daily basis that I bet you already know is organic. What about gasoline? That contains organic molecules. What about cooking oil? Also organic molecules. And do we understand that there's a difference in properties and behavior between organic and inorganic molecules? I think even somewhat instinctively, having lived on this earth as long as you have. I don't think any of that material, at least, is going to be anything surprising to anyone here. Getting back to electron configurations in the periodic table, we said in the second row, we opened up the p subshell. The 2p subshell opens up for business. So there's 3 orbitals in the 2p subshell. 2 times 3 is 6. We can fit in a maximum of 6 electrons. Lo and behold, there's 6 elements. And you can see those orbitals getting filled one by one, going from boron through neon. And the same thing in the third energy level. We've got the 3s and the 3p subshell. The 3d subshell doesn't actually open for business until after we've passed the 4s subshell. It just so happens that the 3d electrons are higher in energy, by and large, than the 4s electrons. But that's where your first d block elements come from. And you can see, even just looking at the periodic table, although we aren't really going to talk about the F block elements, you can see where they go. You can see it skips here from element 57 to element 72. And so that's where the first row of the F block elements comes in. And you can probably guess how many there are in each row without looking. If there were 5 d orbitals and there's going to be 7 f orbitals, 2 times 7 is 14, I guarantee you'll find 14 elements in that row over there. Same thing for this row over here. But we're not ever going to use those elements, the so-called F block or rare earth elements. But you can see where they would go. In fact, you could write the periodic table that way. You'd kind of split it down here, and then move those 2 parts aside, and then take these 2 rows here and stick them in between. It'd look a little funny, but you could do it. It would not be wrong. So Like I said, we're mainly going to focus on the earlier main group elements in this class. So, right. And where all this is relevant to bonding and to putting atoms together to make molecules, which we want to do right quick, certainly by the end of this class, we want to be able to do that. We'll begin to get into structure drawing today, but like I said, changing the material in the class a little bit has given us some extra time, and I'm in no mood to rush here at the beginning. But I think we'll begin drawing some structures by the end of the class, and then maybe on Friday, we'll go over some ways to make structure drawing easier and simpler, take less time. So that, I guess, is what you can mainly look forward to. But be that as it may, all my point for this whole part of the lecture is that the periodic table is laid out in such a way that it almost shouts the electron configurations at you. It's laid out according to atomic electron configurations. That's why it has the shape that it does. So that being said, only there a way for me to put up the periodic table on one and have what I'm writing on the other. Unfortunately, I'm not smart enough at the moment. I guess one way I could do it would be to bring in a physical periodic table and put it on the document camera. I'll try to remember to do that next time if we need it. Although now that I think about it, we almost might not. It might just be that by next time we're already really focusing in on carbon and we don't need the whole periodic table. I will still give you a real periodic table, not the organic chemist periodic table. You will get an actual periodic table with every exam. I would never dream of making you do any kind of chemistry exam without it. But be that as it may, I think we're ready to start talking electron configurations. And like I said, I don't really want to spend half an hour on this, but I just want to remind you how it's done. In Gen Chem, you went over the rules that we use to stick electrons into orbitals one by one. And you learned the smallest element, element 1, hydrogen. You learned that its electron configuration is 1s1. That's a 1, though you'd be hard pressed to know it. There, that's a little better, right? There's only one electron and it goes into the lowest possible energy level. And when we move over to helium, the second element, that's going to be 1s2. And now we have a filled s subshell. And not only that, basically we have all subshell, there's only one, but we have all subshells in the energy level filled. And you'll see that pattern is going to continue for the so-called noble gases or inert gases. Again, I'm going to assume you have knowledge of these terms. You know that each column of the periodic table has a name, and the noble gases are things like helium, neon, and argon. They're in that last column of the periodic table, and the noble gas configurations are important because with those, all of the possible orbitals are all completely filled. And so everybody's happy. And that, by the way, is why noble gases are so inert. They don't want to react. All of their atomic subshells are completely filled. They don't want to either give up or accept any electrons. They prefer just to stay the way they are. No wonder they don't really want to react. No big surprise there. And so we'll do a couple more. The next element is lithium. That would be 1s2, 2s1. And so here already you see the difference between the inner core electrons which are not involved in bonding, and then the so-called valence electrons. Those are the ones on the outermost energy levels, and those are going to be the ones we do in bonding. Not that I think we're going to be forming very many covalent bonds to lithium. Can lithium form covalent bonds? Yes, it's not unheard of. But I think you'll find that in general with the metals, they're going to be forming ionic compounds. And so again, I'm assuming you talked about ionic versus covalent compounds in Gen Chem. And we're not going to have very much to say about ionic compounds in this class. They tend to be inorganic. Oh, I can't tell you that organic ions are unheard of. They do exist. There's a possibility we might meet one or two of them in chapter 13 when we talk about heterocycles, which, by the way, I was thinking on my walk on the way over here. Heterocycle sounds like something you use to get to class. Oh yeah, I'm on my heterocycle. I'll be right there. These words that we chemists are just used to using that are just total nonsense to anyone else. But we will cover heterocycles, and I think you'll find that information helpful later on also when we get to, for instance, nucleic acids and other biological molecules like that contain heterocycles. But my point here being that it's the valence electrons that we're going to focus right in on. That's going to tell us something about how that atom behaves. And so lithium has one valence electron, and not only that, so do all of the elements below it in the periodic table. So does hydrogen, which is above lithium. But you could keep going down: sodium, potassium, and so forth. Those all are going to have one valence electron. The pattern continues. After lithium, we have beryllium, something you don't hear a lot about. I hear it's rather stupidly toxic. I also thought it was used in things like tennis rackets, but something I would want to be somewhat careful with. So there we're going to fill the 2s subshell, and now all 4 of those are inner core electrons. No, that's a lie. I guess the 2s electrons are still going to be valence electrons. After that, we start getting into the first p electrons. So boron would be 1s2, 2s2, 2p1. And so this is going to have 3 valence electrons, and the same 2 inner core electrons. Those 2 electrons in the 1s subshell, that's a filled shell, so we're done with the first energy level. And it's going to become important when we start thinking about connecting other atoms to boron. We need to know that its valence is 3, and that's going to come straight from the electron configurations. That's the main reason I'm talking about this right now. I just want to show you that there's a connection between some of the things you talked about in Gen Chem and some of the ideas we're going to be covering here in organic chemistry. So we could go on. I guess we really need to do carbon since it's organic chemistry. That would, of course, be 1s2, 2s2, 2p2. So that's now going to have 4 valence electrons. And the 2 electrons in the 1s subshell are still going to be inner core electrons. They're not going to be involved in bonding. And then I believe the next noble gas is neon. Just in case I've completely lost my mind, I just want to make sure. Wait a minute. Oh, it's not doing what I want it to do. I've lost my periodic table. I guess because I need to keep it focused on it like that. Yep, neon is the next one. I thought so, I just don't trust myself. So that's going to be 1s2, 2s2, 2p6. And remember, we said there were 3 orbitals in any p subshell, so we can only fit in 6 electrons, so now we're done. Neon is a noble gas, just like helium is. And so no wonder it doesn't really want to react with everything. React with anything. Everything is satisfied. It doesn't need any more electrons, and it certainly doesn't want to give up any electrons. And this pattern continues, by the way. If you compared, we could talk about sodium. It would look very similar to lithium. It would have all the same electrons. Actually, let's do sodium, just because. It would have all the same electrons in neon. And in fact, you can even write, I'm assuming you were taught that it was okay to write any in square brackets. What that means is that it has all of the neon electrons plus 3s1. So that's a permissible way to write electron configurations. Remember that you can only put noble gas configurations in square brackets, right? It's not fair putting Na in square brackets and saying I'm done. That doesn't work. You can only do that with noble gas configurations. Or if you want to write 1s2, 2s2, 2p6, 3s1, it's perfectly correct. There's nothing wrong with it. This is just another way to do it that's a little bit faster. So that pattern continues. Magnesium is like beryllium. What's it called? How can I forget? I'm just blanking out today. I'm a hopeless case. Aluminum, of course. Aluminum is like, I guess I don't use aluminum that much. Aluminum is like boron, silicon is like carbon, and so they will have similar electron configurations until we get all the way to argon, which will be 1s2, 2s2, 2p6, 3s2, 3p6. Or we could write neon, 3s2, 3p6. Or I guess you could also write AR in square brackets. So what does this mean you'll have to know? It means I may put some electron configurations on the first exam. I don't think you'll find 40 questions on electron configurations, but it means it's fair game. Anything in the book is fair game, right? Especially if we talk about it in class. What does that mean you'll need to know about it? It means you might need to provide, well, I guess your exams are multiple choice, so a lot of those sort of questions are moot. But it means you might have to pick out the right electron configuration given an element or an ion, or you might have to go the opposite direction. Best practice you can give yourself is to try to make up your own multiple choice questions. I actually frankly doubt anyone here is significantly worse at making up multiple choice questions than I am. I don't consider myself particularly talented at it. So that's what I suggest you do in order to study for the exam. At least that's one thing I would suggest. I think you'll find the OWL assignments also helpful. They'll give you an idea of possible question formats and possible things you might need to know. Good. So I think that's about all we really need to say about neutral atoms. I would say, and I think I already have said this, but just to be sure, I would say to focus on the neutral atoms and the ions. We'll do some examples of some ions in the S and P subshells. I don't think we'll cover the D block. I'll just mention it quickly here. The one thing you do need to remember about the D block is we have exceptions, right? For instance, the chromium column is an exception. You would expect this to be all of the argon electrons, 4s2, 3d4. That's what you'd expect it to be, counting over 1, 2, 3, 4. But actually it's 4s1, 3d5. I assume you went over that in Gen Chem. And the reason is that there's extra stability. There's a decrease in energy from half filling the D subshell. And something real similar happens in the copper column. You would expect all these elements to be D9. You would expect this one to be argon electrons, 4s2, 3d9. But again, it's actually 4s1, 3d10. So it steals an electron from that S subshell in order to get a completely filled D subshell. It's more stable that way. But the nice thing about that is at least these at least the D block electron configurations are regular. There are exceptions, but they're always the same. All of the chromium column elements do the same thing. All of the copper column elements do the same thing. In the F block, by my understanding, there's no pattern whatsoever. It's just a mess. So that's why I say I'm never going to ask you. I couldn't ask you about the F block elements. I don't know what their electron configurations are myself. So there you go. But I think we're mainly going to be involved with the S and P block elements. The nice thing about the D block elements, should we ever need them, is that although there are exceptions, those exceptions at least are regular. They're always the same, and they include the chromium column and the copper column. So that's pretty easy to remember. What about ions? Ions can also have electron configurations. For instance, if we were to talk about chlorine, the element, well, if you look in the periodic table, this is getting more and more awkward. I seem to have done it again. Got all sorts of extra windows that are not what I wanted them to be. Oh, by the way, I tried to download this image and save it as a JPEG file. You already saw before with the cat pictures what happened. It gave that same error. So I guess I can only use a browser window. Maybe if I did something like that, that might help us out. Let's see, then maybe I'm at least not closing it by accident. Okay, so look at where chlorine is. You see it will have all of the neon electrons, then 3s2, 3p5. So you just get these right off the periodic table. So neon, or again, if you want to write 1s2, 2s2, 2p6, totally fine. Absolutely correct. But then 3s2, 3p5. Well, what about the chloride ion? And why is it that it was always Cl minus and not Cl plus or Cl minus 2 or something like that? That's because when you give it one more electron, of course, electrons are negatively charged, that gives it a negative charge. But when you add just one more electron, that completely fills that 3p subshell. And so you get neon electrons, 3s2, 3p6. In other words, chloride ion has the same electron configuration as argon. And that's why chloride ion is so much more stable than single chlorine atoms. That's the main reason why that is. So my point being, all these letters and numbers that we're writing have actual effects in the real world that you can see with your own eyes. I don't know that we're dealing with chlorine ever. I certainly hope not. It's extremely dangerous. But if we had some and we looked into its behavior, we would see real life, we would see things coming about in real life because of these electron configurations. It's not merely a game that we play with letters and numbers. It actually has real life consequences. So if you want a $60 word to describe that phenomenon of having the same electron configuration, that word is isoelectronic. We say that chloride ion and argon are isoelectronic, or you can say chloride ion is isoelectronic with argon. That's the term we use to mean they have the same electron configuration. And we can keep going. I think you would find very much the same thing with oxygen, or the same type of thing. Here we go. So the oxygen atom would be 1s2, 2s2, 2p4. We just count right off the periodic table. And when you learned your ions in Gen Chem, you don't get it very often, but when oxygen does form an ion, the most common ion by far is O2 minus. There's also an O2 2 minus, that's the peroxide ion, but this is going to be the most common one by far. And that's going to be what you get when you add 2 more electrons. The way you know there's 2 more electrons is because it's got a -2 charge. Where are those charges going to come from except by adding electrons? And so we add the 2 electrons in, and you'll get 1s2, 2s2, 2p6. And you've again got a species that's isoelectronic with a noble gas. In this case, the oxide ion is isoelectronic with neon. It is the same electron configuration as neon. And so that's why you form the ions that you do. It's not arbitrary. There are reasons that we get the ions we do. By the way, and I don't want to get on a tangent. What? Dr. Wass get on tangents? That never happens. Anyway, but I've taught Gen Chem for enough years to know that one of the toughest topics in Gen Chem is ions. And we'll see why when we start actually putting some of these things together. So I think you get the idea about ions. Similarly, you can get cations by taking away electrons. And I think you'll find the goal, you'll get to practice this in the OWL assignment. And I think you'll find the goal with these is going to be always to get to a noble gas electron configuration. I actually took way longer on this than I probably should have. But I think that's at least some good background. Let's see if we can't get at least as far as, I think I've given the basics of ionic bonds. What we really want to get to is the idea of how we use this knowledge to put atoms together and get molecules. Since organic molecules is going to be what we'll mainly focus on. So I don't know why I felt the need to spend 40 minutes on, not 40. Yes, 40. Great, we have 10 minutes left, awesome. We'll make some molecules in our last 10 minutes. Everyone okay so far then? I guess I found electron configurations particularly fascinating today. I'm not really sure why. Good. It's good background anyway. So let's start to consider how it is we start putting these things together to make molecules. And we need to remember that a covalent bond consists of 2 electrons. And the number of bonds that an atom can form is going to have everything to do with its valence, with the number of valence electrons that it has. And so we've talked about how you can tell the difference between valence electrons and inner core electrons. And I don't think it's going to knock anyone's socks off with their shoes on if I show a hydrogen atom with its one electron. We call these Lewis dot structures. That's going to be the 1s electron. And we know that chlorine, like all halogens, has 5 valence electrons. All of the halogens, fluorine, chlorine, bromine, iodine, they all end in something p5. So they all have those 5 valence electrons. Actually, I think I might have misspoken. I think it's, but all halogens will have 5 valence electrons. And so if we put those electrons around that central atom in some reasonably pleasant geometric shape, usually something like this, of course, it wouldn't be wrong to have put an electron pair here and the single electron here. It's the same thing. I only chose to draw it this way so that you can see that we can put those 2 electrons together to form a covalent bond. Now, in your Gen Chem class or your high school chemistry class, you might actually have drawn the molecules like this using just the electrons. I'm not a fan. I'm going to recommend you not do that. I'm going to recommend that if there's a bond between the atoms, that you actually draw a bond as a line. So single bonds will be 1 line, double bonds, 2 lines, and so forth. And I think you can also see that we can easily make methane by taking 4 hydrogen atoms, and not chlorine, whoops, not chlorine, but carbon. And carbon, which has 4 valence electrons. Again, with p block elements, the way you count the valence electrons is it's the p electrons. Whether it's 1, 2, 3, p1, p2, p3, 4, 5, 6, you will then have 1, 2, 3, 4, 5, or 6 valence electrons. I think I might have said that wrong earlier, but your p electrons are going to be your valence electrons. So carbon has 4 valence electrons. Don't tell me I just lied to you again. How badly can I do in one lecture? How many things can I possibly get wrong? Oh, it did it again. Dang it. I don't know what its problem is. Well, anyway, carbon is 4 valence electrons. I'm beginning to lose patience with this thing. So you can see what we're going to get. We're going to get a molecule that has 4 carbon-hydrogen bonds. And that's one way of drawing methane. One thing that I really want to stress here early on at the beginning is that the way to learn this material is not by memorizing what I've written down in class. On the exam, you should expect to be able to understand molecules that you've never seen before. I expect you to be able to look at a structure, even if it's one you've never seen before, and understand it. Understand where the bonds are, understand what the valence is of each of the elements. But this is not going to be done by memorizing every single example we do in class. That might be a start. I mean, I suppose it wouldn't hurt, but that's not the full extent of mastering this material. Good. So, and I would bet that you all came into this class knowing that methane is CH4. No big surprise there. We can go on with this. Carbon can also form single bonds with itself. And so we could take 1 carbon atom, another carbon atom, and then all the other places where we need another bond, we can put hydrogens. And that looks like a dot, but it isn't. There we go. And welcome to the alkanes, by the way. They're a class of molecules that we're going to cover pretty soon. And I think you can see how this is going to work. We're going to have a single bond between the 2 carbons and also 6 new carbon-hydrogen bonds. That molecule happens to be called ethane, though we'll get to that. And when I say about not memorizing what we did in class, and the other point I'm making, which is there's many, many correct ways to draw any one molecule. Maybe today you felt like making this molecule vertical. Fine. It's absolutely correct. So they're the same molecule. And you can turn any structure any given way. So I would say that's also part of what it means to have mastered this material, that you recognize the type of molecule and recognize where the bonds are, no matter which direction it's pointing. One of you told me the other day that you had a chemistry teacher once who said, no, you have to draw it exactly the way we're drawing it here. If anyone ever told you that, they were lying. It's not true. The molecule can face any direction, and it's the same thing. So the successful student will be able to recognize that those are the same molecule. They're just different ways of drawing the same thing. It's not a different molecule. And that comes with practice. But this is also why carbon is special and why organic chemistry is its own field, focusing on molecules that overwhelmingly take their properties from having a certain amount of carbon and hydrogen in them, because we get these stable bonds between carbon and other elements and between carbon and itself. The same is not true for silicon, by the way, even though silicon is right below carbon in the periodic table. So all of those old B science fiction movies with silicon-based life forms, it's probably a bit far-fetched. I think I'm no cosmologist, but my understanding is that most cosmologists agree today that silicon-based life is probably not a thing. There's something special about carbon. What about bonds to other elements? Well, we could go on. I think if we do just a few more examples, that will, yeah, and we'll end just about on time. What if I wanted to take two carbons again? And maybe this time we'll put in an oxygen. Oxygen is 6 valence electrons. 2s2, 2p4, right? So there should be a total of 6 electrons, which is good. That means that means I was lying about lying. That means that what I originally said to you is true. So we're in good shape. Good, but we want to get, remember, we want to get filled subshells. We want all electrons to be paired. We don't like having species with unpaired electrons. Those tend to be unstable. And you can see what we're doing here. We're going to have a grand total of 5 new bonds between carbon and hydrogen, 1 new carbon-carbon bond, 1 new carbon-oxygen bond, and a new oxygen-hydrogen bond. And so the molecule you get happens to be called ethanol. We'll learn how to name molecules as we go, as we cover each functional group. This is the intoxicating component in adult beverages. So I'm sure you've heard of this molecule. And so we would draw the structure like this, or you could just as easily draw it like this. That actually brings up another point. I'm not going to forget my lone pairs. A question I very commonly get at this point is, will we lose points if we don't put in the lone pairs on atoms? Well, again, your exams are going to be multiple choice. So questions like that are kind of moot. But if I had to give an answer to that question, I would say, let's, at least through the first exam, let's always put non-bonding lone pairs in. And so the reason oxygen has those lone pairs is they were part of its valence electrons. But oxygen also had 2 unpaired valence electrons. And so we needed 2 more electrons around it in order to to have the octet rule fulfilled. And we'll have a lot more to say about the octet rule next time. This, by the way, isn't even necessarily the usual way that I will recommend you draw structures. I'm just trying to set up the idea of drawing structures. I still have a couple of minutes, so I want to point out some examples of compounds with double bonds. I think we might already have looked at carbon dioxide. CO2 would look something like this. And you'll notice that carbon is obeying the octet rule, right? Carbon is an atom that obeys the octet rule, 2, 4, 6, 8. So there's 8 electrons around carbon. And not only that, but also the oxygens obey the octet rule. We'll have more to say about the octet rule next time, but 2, 4, 6, 8. So most atoms obey the octet rule. There are some notable exceptions like hydrogen, right? Hydrogen only has 2 electrons around it. What might be another example of a molecule with multiple bonds? What about hydrogen cyanide? And we'll end with this. So triple bonds are allowed also. There's now a triple bond between carbon and nitrogen. And I will say also, this maybe is a good thought to end on, quadruple bonds are not a thing. We will not have quadruple bonds, but single, double, and triple covalent bonds exist. In terms of a more general way to be able to draw structures using a nice step-by-step method, we'll start with that the next time when we get into structure drawing in earnest. Other than that, have a great day. I will see you all on Friday.